If you have a different calculator, then it may not be the same directions. If you need help with your other calculators, send me an email. We'll figure it out. So we are looking for number 0, the binomial PDF. Note, there is a binomial CDF. The C stands for cumulative. It adds several numbers of successes, the probability for several x's together. We don't want CDF. We want PDF. So when you have the 0 highlighted, you'll press enter, and it'll bring up binomial PDF. So now we just enter the pieces. So first we enter n. We had 5 trials. And now we have to separate all these inputs with the comma, which is above number 7. So we put in n, 5, comma. Now we put in p, the probability of success, which in this case is 1/6. So we can do 1 divided by 6, comma. And then lastly, little x. How many successes do we want? Well, we wanted 3. You don't have to put the closing parentheses. You can just press enter. And you get 0.0322, which is just what we got by doing it by hand. Okay, pretty neat. We can check a couple more of these. So say we wanted the probability that x is 0, so that should be 5/6 to the 5th. Okay. So if we do that by just manually calculating that, so we have 5/6 to the 5th, so we get 0.4019 if we round it to 4 spots. Or we can use the binomial PDF. So here we would say that we have 5 trials. The probability of success is still 1/6, but now we want 0 successes. So every time you use the binomial PDF, if you were to use it multiple times for a particular distribution, all that's changing is the little x. N stays the same. You always have the same number of trials. Your probability of successes always stays the same. It's always 1/6. So we're just changing the little x. So let's type that in. So we're going to press second, vars, and then if you know that binomial PDF is number 0, you can just press 0. And it'll bring you right to binomial PDF, and you don't have to scroll through it. You can still scroll through and select it also. So we want n to be 5, we want p to be 1 divided by 6, but now we want 0 successes. And again, we get 0.4019. So we get the exact same thing. Okay. So let's do the probability that x is 1, and then we'll move on, I think. So for the probability that x is 1, we had 5 times 1/6 times 5/6 to the 5th. Or sorry, 5/6 to the 4th. Okay, so really what this ends up being is 5 times 1/6 is 5/6. 5/6 times 5/6 to the 4th, well, that's just 5/6 to the 5th. So this is just like the probability that x is 0. This should be 0.4019. So let's enter that into the binomial PDF. So there's kind of a shortcut. If you need to use this binomial PDF again and again and again, you don't have to go back through the second vars menu to find it. If you want to repeat the last function that you entered, if you look above the enter key, it says entry in yellow. So if you press second enter, well, it didn't work that time because I deleted it. But usually it will bring back, there we go, it will bring back the last function you entered. And then once you've brought it back, you can use the arrow keys to scroll through and change stuff you want. So all I'm doing is I'm changing this to 1. So however you get there, You can go through the menus or you can use the shortcut. We want binomial PDF, n is still 5, p is still 1/6, and now we want 1 success. Press enter, and you see that we get the exact same value. Okay. And we could use this to fill out the whole distribution, but maybe we'll save that for a different problem. Okay, so basically the idea here is, under certain circumstances, we can use this binomial PDF, and it just saves us a bunch of time. So the important thing is, when can you use this shortcut? So there are a couple of, I tend to call them assumptions. So first, you need to have 2 outcomes. One is a success, one is a failure. That's it. You can't have more than 2 outcomes. Second, you have to have independent trials. So what this means is, kind of the implication here is that the probability of success as well as the probability of failure remain constant across all of the trials. So this is like coin flips, rolling die, doing selections with replacement generally. Any type of independent trial is okay, as long as you have 2 outcomes. That's kind of the second piece. When you do the MyStatLab problems, they'll add in like a third assumption, which is kind of implicit, which is that you're doing this over several trials. So essentially you're doing it more than once. If you're doing this once, it's not really binomial, it's more of this Bernoulli experiment. If you're doing this over several trials, basically n is something bigger than 1. Then you have the binomial distribution. So if these 3 assumptions are true, then this means that your big X, whatever you're interested in counting, follows a binomial distribution. Okay? So let's do an example. Well, I guess before we do that, we'll look at what is the binomial distribution. So, thinking back to chapter 2, we described probability distributions. We looked at their shape, their center, and their spread for different types of measurements, like heights or weights or something like that. Well, how is a binomial random variable distributed? It's not like a height or a weight. It's counting the number of successes. So what's a distribution of successes look like? And the answer is it depends. Okay? So in these 9 examples, they're almost all the same. So in all of these, we're going to have 10 trials, but we're going to change P, the probability of success. So it's going to change from 0.1, so a 10% chance of success, 0.9, a 90% chance of success. So maybe the first thing to look at is this weird statement here. X, squiggly line, B, 10.1. So this, we can translate this. This is essentially saying that X is distributed as, that's the squiggly line, so is distributed as, that's what that little squiggly line means. B means it follows a binomial distribution. The first number is n, so with 10 trials, and the second number is p, the probability of success. P is equal to 0.1. So when you see this statement, this means that your random variable follows a binomial distribution with 10 trials and a 10% chance of success. And that's just an abbreviation for all of that. So what we have in this bar chart, this distribution, is on the bottom we have little x. So that's the number of successes. So you see that it ranges from 0 to 10, because we have 10 trials, so we can't have more than 10 successes. And on the y-axis, you have this notation f of x. Don't worry about that. Think of this as the probability. So the height of this first bar, that's the probability that you would have 0 successes. The second bar, that's the probability that you would have 1 success, probability of 2 successes, 3 successes, all the way up to the probability of 10 successes. So you'll see that this distribution is right skewed, pretty severely maybe. And this makes some sense. So what we have to keep in mind is that we have 10 trials, and in each of them there's a 10% chance that they will be successful. So then what you want to think about is, across those 10 trials, how many successes would you see? Well, you're not going to see, likely, all 10 successes, because there's only a 10% chance for success. It's pretty hard to get a success. So what that means is you would expect to see just a few successes. In fact, maybe you can see that out of 10 trials with a 10% chance of success, you would expect 1 success. And that's this tallest bar, 1, is the mean. That's the expected number of successes. So you see that it has the highest probability, but it's really not that big of a probability. It's less than 40%. You're also pretty likely to have 0 successes, less likely to have 2, and it drops off. So there are bars here. They're just extremely close to 0. They're not equal to 0. It's not impossible to have 10 successes. It's just unlikely. So what we can observe is what happens as we increase the probability of success. So we go from 10 to 20 to 30 to 40 to 50%. So here we have kind of a bell curve. And we see again the tallest bar is at 5, which is the mean. So if you have 10 trials and a 50% chance of success, then you expect half of them to be successful. 5 out of 10. So that bar is the tallest, but again, that's not a guaranteed result. You're about, 22% likely to have 5 successes in 10 trials. Okay? So this you might think about as the probability distribution for flipping a coin 10 times. And you could be interested in heads or tails. How many heads do you have in the 10 flips, or how many tails do you have? It doesn't matter. So you're counting up how many heads or tails you have. You expect 5. You could get more. You could get less. It is possible to get all 10. It is possible to have none of them be your result of interest. And then as the probability of success keeps increasing up to 0.9, now we have a left skewed distribution. If the probability of success is large, then you would expect to see lots of successes. So the binomial distribution in general does not have a particular shape. It depends on its parameters. So it depends on n and p. So let's do an example. So a hospital wants to evaluate the success of their cardiology program by looking at the number of successful heart surgeries in the last year. And they see that the probability that a patient recovers is 90%. Assume that the surgeries are independent, which is reasonable. So what that means is the outcome of one surgery doesn't affect the outcome of another. So essentially this is true as long as you have multiple surgeons. However, good or bad, the first surgery went, the next surgery should not be affected. Maybe if it's the same surgeon, but we will assume there are several surgeons. And the next week we have 7 surgeries. So the first question is, how many of the next 7 patients can we expect to recover? Well, you may start to notice some things here. So the first thing is, well, let's define our random variable, what we're looking for. What is big X here? So in this scenario, we're interested in the number of recoveries in the next 7 surgeries. We're told that surgeries are independent, so that means a trial is a surgery that's generating the outcome, recovery or not. And we're told that these are independent. And then as we just explained, we have 2 outcomes. We have that the patient recovers, so we can think of that as our success. And we have that they don't recover, so we can think of that as our failure. Okay. And from how we define the random variable, this tells us that we have multiple trials. So we have 7 trials, 7 surgeries, and we're told that the probability that a patient recovers is 90%. Well, that's the probability of success. We want recoveries,